set, we're only looking at 2 in class, but you'll have the solutions for all of them, right? And you'll need these problems for the homework that's been assigned today. All right. The first problem that we're seeing is that you have this package that is thrown down this incline with a velocity of 1 meters per second along this incline, right? And it slides along the surface ABC to a conveyor belt, which is moving at a velocity of, the conveyor belt itself is moving at a velocity of 2 meters per second, right? And you're told that this distance d down the slope is equal to 6 meters, and you're told that this distance from B to C is 7 meters, and you're told that there's a kinetic friction term that's coming in, where mu k is equal to 0.2 between the package and all of the surfaces that you see over here. And what you're asked to do is to find the speed of the package at the point C, which is it just comes on to the conveyor belt. And you're also to ask the distance the package will slide along the conveyor belt before it comes to rest, right? In essence, what that means is it just starts moving at the same velocity as the conveyor belt. All right. Okay. So what the first part of the calculus is asking you to find the speed at the point C, right? So we can do this problem looking at the work energy principle, right? Because what you can do is, so let's say that this is the position A, and like that, right? Where B and C over here. That what you can say is when you move on to position C, you can express everything in terms of your work energy expression, right? So you can say that the initial kinetic energy, right, plus the work done to move from A to B. Actually, you will write it out as the work done from moving to A to C, right, is going to equal your kinetic energy at C, right? But because, it's at an incline here, and then it's going to be horizontal over here, you can break this term up. You can say that TA is going to be from A to B plus the work from B to C plus equaling your kinetic energy at TC, right? So these work dones we'll have to find after looking at our free body diagrams, right? TA we know, right? Because we know what the velocity is at A, right? We're told that it's 1 meters per second. So this guy here is known. This is the unknown, right? Because this is going to equal the velocity of the package, which we need to find, right? There's going to be half m VC squared, and this VC is what we have to find, right? What part A of your question is. These terms we can figure out pretty easily using Newton's second law. All right, so let's take a look at that. So for position A to B, if I look at the free body diagram, so let's say we're looking at A to B first, right? Looking at your free body diagram, what are all the forces that act on it?
Your weight, normal force, and friction force.
There we go. So you got your weight, right? You'll have your normal force, right? AB, like that. And you'll have your friction force, right? So you have F, let's call that friction force FAB, right? Opposite direction in which you moved in. And also, we know the angle of the incline is 30 degrees, right? And we know that FAB has to be found in terms of the reaction force, right? So first expression we can write straight away is that the normal force is equal to, and again, we're, coordinate system, X, Y, like that, right? It's implicit in our conversation now. I expect you guys to do this. So NAB is equal to what? mg What is it equal to?
mg cos theta.
Mg cosine theta, right? Mg cosine, this because this angle is going to be 30 degrees as well. So mg cosine 30, like that. All right. Now, we can't do a force equilibrium along this x direction because, you know, there might be movements and things like that. So we just have to find all of the forces in that direction. So next, we say that FAB is going to equal mu k times NAB, right? So that's going to equal 0.20 times mg times cosine of 30 degrees, like that. Right? So what are the only forces that are going to be doing work when you move from position A to B?
Friction force and weight.
Friction force and weight. Absolutely 100% right. All right. And the weight work is going to be positive because it's in the same direction. And for the friction force, it's going to be negative. So what you end up with is mgd. And it's the component of the weight in that direction, right? So it's sine theta like that minus FAB little d. And here, remember what little d is, right? D is just the position from A to B, the displacement that happens like that. So that's what you end up with. So you end up with basically mgd times sine of 30 minus nu k times cosine 30 like that. And we know everything in this expression. All right, next, we're looking at B to C. Like that, right? So if we look at the free body diagram there, same thing, right? Normal force, weight, and friction force. But now you have things moving in different directions. So you have mg like that. You'll have a normal force, NBC like that. You have friction force, FBC like that, right? So here, NBC is just going to equal mg, right? And the displacement that it moves, let's say that this guy is just equal to xbc, like that, right? So we know what it is. Then you could say that your friction force FBC is just equal to mu k times mg, like that, right? Normal force is equal to mg. So your work done from moving from position B to C is going to be negative. In general, work done by friction is always negative, right? So minus mu k times mg times this distance xbc that we've defined over here, the horizontal distance, which is known, right? Technically shouldn't call it xbc, but oh well. And again, everything here is fully known. All right, and we're done. That's it. Just plug everything back into this expression here and solve for VC. So you end up with TA, which is, all right, let's number things so that you guys can follow. So let's call this expression 1. Let's call this expression 2. Let's call this expression 3. So from 1, 2, and 3, you end up with half mVA squared plus mgd times sine, whoops, 30 minus mu k cosine 30 minus nu k mg xbc is equal to 1/2 of m vc squared. All right, so what was m? Basically, you guys get the idea, right? So, and you can, everything is known except vc, right? So I'll let you guys figure that out. Solve for vc. everything else is known, right? So VC ends up being, the answer that I have is 4.65 meters per second. Questions,
Sorry, quick
guys?
question.
Yeah.
Sorry. Yeah, for the displacement for the free body diagram from ATB, is it in different way?
Is it what?
Like, is it going down, like
Yeah.
for the displacement?
Yes, it's going down.
Yeah. Wait, was that you drawing it upward?
Did I
For the
draw it
X?
upward?
Yeah.
No. Where did I draw the displacement upwards?
Wait, so is it like, so the FAB is going to be the same direction with the X side, right?
FAB is the friction force. It's in the opposite direction to the motion. The motion is this way. It's down like that. And here, the motion is like that. Did I answer your question?
Oh, okay, got it.
FAB is the friction force. All right, let's write that out. This is friction. Friction opposite to the motion. Here again, this is friction opposite to the motion, right? This component of the weight is in the same direction as your motion. Therefore, it is positive, mgd sine 30 degrees, right? That's what we looked at today. This is in the opposite direction. So that's why it's negative here. Signs are important, right? I hope I answered your question. Thank you.
Another quick question, if I may.
Yeah, of course.
So in equation 2, you have, when you substitute FABD into there, I was curious what happened to the 0.2 or the, oh, you already wrote it. You just left
It's
it
right
as
there.
simple. Never mind. I just answered my own question.
Yeah, it's right there. It's right on top. Yeah. Just have to be careful, guys. It's pretty straightforward. Any more questions, guys? All right. So next part of the problem is you're asked the distance the package will slide on the conveyor belt before it comes to rest relative to the belt, right? So what's the velocity going to be when it comes to rest on the belt?
A few meters a second.
Right. Why is it 2 meters per second?
Because that's what we're given.
That's what the belt is moving at, right? So even though it's relative rest to the motion of the belt, doesn't mean that the kinetic energy is going to be zero because the belt is moving. What is velocity at end of belt, at end of sliding? Right, it's going to be V equals V belt, which is equal to 2 meters per second, like that. Right, and again, we've already looked at the work energy principle, right? So what we can write our expression straight off is kinetic energy at position C plus the work done for moving from position C to, let's say, rest, like that, right? Is equal to your final kinetic energy. So that's going to be the kinetic energy. Let's call it, I don't want to say belt because that's the kinetic energy of the belt. Kinetic energy, end of sliding. You know, rest is bad. All right, guys, give me 1 second. EOS is equal to end of sliding. So C to EOS, T EOS. Does that make sense? You guys understand that? All right, good. So initial kinetic energy is 1/2 mVc squared, right? We know this. We found this out from the previous part. We also know the work done and sliding horizontally. It's going to be the same because the friction is the same, right? So it's going to be this expression over here. So it's just going to be minus nu k mg times whatever the distance is that it moves on the belt before sliding, right? So this is the guy that we're trying to find, right? Everything else is going to end up being known. Plus your kinetic energy at the end of sliding, which is the kinetic energy due to just the motion of the belt, right? So everything else is known except for this one term, one expression, one unknown. The final answer that you end up getting is 4.49 meters. So what I mean by giving you 95% of your marks for setting up the problem is, if you give me number of expressions for number of unknowns, and those unknowns are correctly related to your problem, and the expressions are correctly related to your problem, you're going to get 95% of your grade for the exam, in the exam. All right. So setup more important than solving. All right. This part, you guys are like, you know, you're pretty far advanced in your engineering career that I expect you to just close your eyes and be able to solve things like this. All right. Okay, let's look at last question. Well, before we go on, any questions with this one? This was pretty straightforward, right? Okay, let's go on to the last question. Ooh, this one I like. All right, so you have a small block which slides at a speed v on a horizontal surface, right? And we're assuming there's no friction. You know, you only take friction in the picture when the problem tells you that there's friction. Why make life more complicated for yourself, right? So knowing that this height h is equal to 0.9 meters, you're asked to find the speed of the block if it is to leave the cylindrical surface BCD when theta is equal to 30 degrees. All right. Okay, so now to do this problem, we can say that when we're moving from position B to this position C, right? So you can say that the kinetic energy at position B plus the work done from moving to B to C is equal to the kinetic energy at position C, right? So if we write these things out, what's the kinetic energy at position B? We know the velocity at position B, right? So let's just write it out as half m VB squared. All right, let's write these out one by one. So B is equal to half m VB squared. All right. Work done from moving from position B to C is going to equal what?
Velocity times the arc length.
No. The work done is going to equal in terms of the things that you have, right? What is the only force that's doing work here, guys? Recall your pendulum problem.
Gravity or weight?
Gravity, right? So what's the work done from B to C going to be? It's basically going to be your weight times the change in vertical distance, right? Is it going to be positive or negative?
Positive?
Positive. right? Because the weight is in the same direction as your motion. So now the trick is, how do you find the change in vertical in distance, right? You can find it out. Say hello to Triangle Boy. You have that height equal to h like that, right? And then how do we find change in vertical distance? It's going to be matched. So cylindrical surface, this is a circular arc, right? So this distance here is also going to be h like that, right? So this distance here is going to be h cosine theta, right? So this distance here is just going to be h minus h cosine theta. So h times 1 minus cosine theta. Is that clear? Guys?
Yes.
Yep.
Okay. So this, everything is known. mgh times 1 minus, and see, we're getting closer and closer to what you guys know and love with potential energy and stuff like that. But no, we're not calling it potential energy. It's work done right now. So it's mgh times 1 minus cosine theta. All right, this is the velocity that we're trying to find, right? So next, you have your velocity with which it's at this point over here, right? So you have half m vc squared. This kind of muddle things up because now you have two unknowns in this expression. How can we go about fixing that problem? All right, guys, this is like a standard thing in our class, but we're going to go 5 minutes over. All right. So it's like, you know, you had the false hope from the first class that we end early. That's never going to happen ever again. So how do we go about fixing that problem? What can we do? What more expressions can we get? All right, think about this thing. When it loses contact, what happens to your forces over here? Right, so at any random position between B and C, if I draw the free body diagram out, what do I have, right? I have my weight always acting downwards. I have my normal force, right? And that's going to act at some angle theta, right? So at position C, what's going to happen?
Lose contact.
Normal.
with the
No.
surface.
You lose
Normal.
contact and your n is going to become 0, and you can use that to find out what VC is. How do you do that? How do you find out what VC is? Newton's second law. Use your kinetic diagram, right? How does that help you out? You guys are asking me. Well, remember normal and tangential components? Right? What's AN equal to? What's the normal velocity equal to? The normal acceleration equal to when you're using normal and tangential?
0 because it's normal to the.
No. Nope. Forget this part here. We're only looking at this part. When you're looking at normal and tangential components, what's your normal acceleration equal to?
Do we have an origin?
No, you don't have an origin. You're looking at normal and you're looking at the path. You're looking at normal and transverse components. Normal and tangential components. Excuse me. Guys, a normal and tangential component, what's the normal acceleration equal to? Yeah, v squared over rho, right? At the point C, that's going to be vc squared. What's rho? It's just h. It's a circle, right? This is going to be your radius of curvature. So v squared h, like that. Right? And now if you write your expression out in the normal direction, right? So if you define your normal direction to be like that, right? You get that n minus mg cosine theta is going to equal mvc squared over h, like that. But we've said at the point of it loses contact, that guy's equal to 0, right? So you find out an expression for your velocity. Vc squared is just equal to gh times cosine theta. And that's it. 2 expressions, 2 unknowns, problem solved. Is that clear, guys? So now when you write out your energy expression, this is 2, this is 1, right? Now you have 2 expressions for 2 unknowns. You end up with the expression half mvb squared plus mg times 1 mgh times 1 minus cosine theta is equal to half times m times vc squared, but we know that that's just gh cosine theta, so I'm just going to write that out over here. And that's it. Only one unknown here. Everything else is known. All right, so you solve that, you get that your VB ends up being equal to 2.30 meters per second. So basically, for all of these things to happen the way they did, you need to slide your thing off at 2.3 meters per second. Good. Now, the thing to note is that the solutions that we post online are the book solutions, and they don't have this sometimes this clear way of thinking. This is, a clear way of thinking is setting up your expressions, unknowns equals the number of expressions, always. All right. Yes, there is TA help tomorrow from 5 to 6 p.m. Well, we should update the invitation. Thanks, guys. See you in class. 235, 235 JMC and 242 JMC. But I think we're going to consolidate everyone into 235, or we'll take it there. But see you guys sharp 9:15 a.m. on Thursday for the exam. All right.
Thursday.